Okay, so now we're ready to connect these essentials of linear algebra to our original question, which was solving some system of differential equations. So recall we were working with a system of differential equations that was linear and had constant coefficients. And what we started off saying was we can predict that these solutions would look something like this. They would have a form where they are e to the r1t plus e to the r2t, both for x and y. And they're going to be interdependent on each other. So these constants c1 and c3, c2, and c4, they are all going to be interdependent possibly. And when we plugged these solutions over here into the original differential equations and grouped things around, we set up conditions that this power R1 would need to satisfy. And that was over here. So what we found out was if R1 satisfies this system over here, then it should appear as one of the powers in our solution. Okay, so these values A, B, C, and D, they come from the original coefficients in the differential equation. C1 and C3, that's going to be the arbitrary constant that we have in front of the e to the r1t term. So now we can take that system and rewrite this as a matrix equation. So I could write this as A, the matrix, 2 by 2 matrix, A, B, C, D, times the column vector C1, C3, and that should equal the scalar R1 times the vector C1, C3. So there's one condition that we get for R1, and we can do the similar thing with the conditions that we found for R2, which were pretty similar, and in that case, we would still get A, B, C, and D, this 2 by 2 matrix of coefficients, and the only difference here is these column vectors involve the coefficients C2 and C4, which are the arbitrary constants in front of the e to the r2 exponential term. And if you look at these for a second, and if you've had some linear algebra, maybe you recognize these conditions. So what this means over here is that R is an eigenvalue of this matrix. And C1, C3 is the eigenvector of that eigenvalue. And same goes over here. So R2 is also another eigenvalue of the same matrix, and this is its eigenvector. So if you are not familiar with these terms, eigenvalue and eigenvector, I define them more carefully on the next slide. I'm not going to make a video for that slide. You can read through it, and there's a whole bunch of material in the reading materials that go through in more detail how we can find eigenvalues and eigenvectors. I'm going to do plenty of examples that show how we can do these in the context of solving systems of differential equations. But the main takeaway here is how do we find the values R1 and R2? We need to find the eigenvalues of our matrix of coefficients. So let's continue on to talk about how we can set up the matrix of coefficients for a differential equation.